In the depths of space where darkness and light converge, the James Webb Space Telescope, JWST, has revealed an astonishing scene that challenges our preconceptions about the universe. A mysterious, unusually bright object appears in a deep field image, its form and luminosity defying standard expectations. As photons from this remote beacon travel billions of years, they carry a story of cosmic evolution that forces us to question the nature of matter and energy at the universe's very dawn. This discovery is not simply a matter of astronomical record, it signals a need to re-examine our models of cosmic structure, dark energy, and the interplay between gravity and the forces that sculpt the cosmos. As scientists scrutinize this bright anomaly, the intensity and unusual shape of the object spark a mixture of awe and skepticism. Its brightness suggests it might not be a conventional galaxy but possibly an entirely new type of astrophysical entity, one that demands a rethinking of how cosmic light is produced in the early universe. The object's unique properties raise the possibility that we are witnessing phenomena, whether transient events, primordial relics, or exotic manifestations of matter, that do not fit neatly into the established framework. Each new observation serves as both a clue and a challenge to our theories, hinting at processes that may be as extraordinary as they are unknown. The conventional picture of cosmic expansion, long held as a steady and uniform process, is now under renewed scrutiny. JWST's data indicate that the universe's expansion might not be as homogeneous as once believed. In some regions, the expansion appears to be anomalously rapid, while other areas lag behind, suggesting a complex interplay of forces. These irregularities prompt us to consider whether local variations in dark energy density or previously unrecognized gravitational effects are at work, thereby transforming our understanding of spacetime's evolution. What once was seen as a predictable cosmic swell now hints at a more nuanced and dynamic process, one that could force us to rewrite the laws governing the cosmos. Observations have also upended our timeline for galactic evolution. In a twist that defies traditional models, spiral galaxies, once thought to require billions of years to take shape, appear with surprising frequency in the early universe. Nearly 30% of galaxies observed merely 2 billion years after the Big Bang exhibit well-defined spiral structures, contradicting the slow, chaotic assembly predicted by standard theories. This revelation invites us to explore alternative pathways in galaxy formation, perhaps involving more efficient processes of angular momentum distribution and rapid gas cooling, thereby reshaping our understanding of how order emerges from cosmic chaos. Equally perplexing are the objects that refuse to be neatly categorized as galaxies. JWST's deep field surveys reveal a population of small, luminous entities that seem to vanish from our later observations, leaving behind a mystery about their origin and fate. These objects might represent transient phases of cosmic evolution or entirely new classes of astrophysical bodies that played a crucial role during the universe's formative years. Their apparent absence in the nearby universe deepens the enigma, suggesting that the early cosmos hosted phenomena that were both fleeting and fundamentally different from the structures we see today. As the body of evidence grows, the very foundation of the Big Bang model is called into question. How could such complex structures, spiral galaxies, massive black holes, and unclassifiable luminous objects, emerge so rapidly in a universe only 14 billion years old? This conundrum has led some of the most respected astrophysicists to speculate that the Big Bang may not have been the singular explosive beginning we once thought, but rather one phase in a cyclical process of cosmic creation and destruction. In this view, remnants of previous cycles or even pre-Big Bang phenomena might be subtly influencing the structure and evolution of our universe today. One of the most riveting puzzles arising from these observations is the existence of supermassive black holes in the very early universe. Traditional theories struggle to explain how objects of such immense mass could form in such a short span of time after the Big Bang. Some researchers propose that these black holes might have originated from primordial seeds that predate the conventional start of cosmic time. This possibility forces us to confront the idea that gravitational collapse and rapid mass accumulation may have been active under conditions far more extreme than those predicted by our current models, suggesting an evolutionary timeline that is both surprising and profoundly complex. The redshift data emerging from JWST has forced us to re-examine cosmic chronology itself. For example, the potential identification of a galaxy with an extremely high redshift implies that complex structures were forming a mere 160 million years after the Big Bang. Such early appearances demand that we reconsider the timescales of star formation and galactic assembly. The rapid emergence of well-formed systems implies that the physical conditions in the early universe were far more conducive to structure formation than previously believed, urging a thorough re-evaluation of the initial moments of cosmic history. At the heart of these mysteries lie the twin enigmas of dark matter and dark energy. JWST's revelations suggest that variations in dark matter density and the enigmatic influence of dark energy might be responsible for the unexpected structures and expansion rates observed in the early universe. Far from being mere background players, these elusive forces may be actively sculpting the cosmos in ways that defy our current understanding. As we delve deeper into the data, it becomes clear that any comprehensive model of cosmic evolution must account for the dynamic interplay between the seen and unseen, revealing a universe where even the darkest components illuminate profound truths about existence. The cosmic web, a vast, interconnected network of galaxies and dark matter, reveals even more intricacies when observed through the lens of JWST. What was once considered a relatively uniform scaffold of matter now appears as a dynamic tapestry, richly detailed and far more complex than our simplified models suggest. The filamentary structures and vast voids indicate that the processes of galaxy formation were active and finely tuned from very early on. As we map these cosmic filaments, we see evidence of gravitational interplay and dark energy's counterbalancing force, each thread in the web contributing to a picture of the universe that is as beautiful as it is bewildering. Beyond our familiar dimensions, hints of extra dimensions or parallel universes are emerging from the depths of JWST's data. Some of the peculiar properties of early cosmic objects have led researchers to entertain the possibility that our universe might be only one slice of a multidimensional reality. The suggestion that gravitational effects, dark energy variations, or unusual brightness levels could be influenced by factors beyond our conventional three-dimensional space is both radical and captivating. Such ideas, rooted in advanced theories like string theory and brain cosmology, challenge us to expand our conception of reality and to consider a cosmos that is far richer and more layered than we ever imagined. The notion of cosmic recycling has gained renewed vigor in light of recent discoveries. Far from being a one-time event, the Big Bang might be part of an endless cycle of creation and destruction. Observations of ancient galaxies and supermassive black holes hint at a scenario in which the remnants of a dying universe, perhaps in the form of primordial black holes or residual cosmic energy, ignite a new era of cosmic birth. This cyclic model of cosmic evolution challenges the linear narrative of time and invites us to imagine a universe in perpetual renewal, where each phase of cosmic history lays the groundwork for the next. These discoveries also prompt us to rethink the nature of time itself. Traditional views of time as a linear progression from a singular beginning to an eventual end may be overly simplistic when faced with evidence of rapid, cyclic, and overlapping epochs in cosmic history. The early emergence of structured galaxies, the fleeting existence of unclassifiable luminous objects, and the implications of a pre-Big Bang era suggest that time might be more fluid and relative than our everyday experience would indicate. This opens up profound questions about causality, the directionality of time, and the fundamental processes that govern the evolution of the cosmos. The interplay of countless cosmic forces can be likened to a grand symphony, with each instrument, be it gravity, dark energy, or the quantum fluctuations of the early universe, playing a critical role in the creation of cosmic order. Every observation made by JWST adds a new note to this symphony, revealing subtle harmonies and dissonances that challenge our understanding of the underlying score. For the expert astronomer, this interplay is a call to listen deeply to the rhythm of the cosmos, to decipher the underlying principles that govern the emergence of order from the primordial chaos. As we peer deeper into space, we approach the very edge of the observable universe, a boundary defined not by a physical barrier but by the limits of light and time. The deep field images captured by JWST extend our vision to the furthest reaches of cosmic history, where the earliest stars and galaxies began to form. Yet, even as we gather light from these distant epochs, we are reminded that there remains a realm beyond our observational horizon, a dark, uncharted frontier that may hold answers to questions we have yet to ask. This edge is both a limit and an invitation, urging us to push the boundaries of technology and theory in our quest to understand the universe. The theory of cosmic inflation, long held as a cornerstone of modern cosmology, is undergoing vigorous re-examination in light of the new evidence. Observations that reveal unexpected uniformity and rapid structure formation suggest that the initial burst of expansion may have been more complex than a single, explosive event. Instead, the inflationary period might have featured multiple phases or fluctuations that set the stage for the intricate cosmic tapestry we observe today. This nuanced view of inflation compels us to refine our models of early universe physics and to explore how quantum fluctuations during inflation could have seeded the vast cosmic structures that now surround us. Delving into the quantum fabric of the cosmos, we find that the seemingly random fluctuations at the smallest scales may have left an indelible imprint on the grand structure of the universe. JWST's observations hint that the early quantum behavior of matter and energy played a pivotal role in shaping galaxies, clusters, and even the cosmic web itself. The possibility that quantum effects are not confined to the microscopic realm but extend their influence across astronomical distances challenges us to bridge the gap between quantum mechanics and general relativity, ultimately revealing a universe where the rules of the very small and the very large are inextricably linked. One of the key breakthroughs enabled by JWST is its advanced spectroscopic capability, which allows us to analyze the chemical fingerprints of distant cosmic objects in exquisite detail. By dissecting the light from ancient galaxies and luminous bodies, scientists can determine the composition, temperature, and motion of these objects, uncovering clues about the processes that govern their formation. The spectral signatures reveal the presence of elements forged in the crucibles of the first stars and hint at physical conditions that differ markedly from those of the local universe. This powerful technique not only confirms redshift measurements but also enriches our understanding of the evolutionary pathways of cosmic structures. The established paradigm of galaxy formation is being rewritten by these groundbreaking observations. Rather than a slow, gradual assembly over billions of years, the early universe appears to have been a crucible of rapid, efficient formation. Massive spiral galaxies, structures once thought to require extended periods to evolve, are now seen emerging in what appears to be a remarkably short cosmic timeframe. This rethinking forces us to consider alternative processes, such as rapid cooling and fragmentation of primordial gas clouds, and to explore how the dark matter halos might have accelerated the formation of these orderly systems in an environment that was anything but calm. The dynamic dialogue between observation and theory is more evident than ever. Each unexpected finding, whether it is an anomalous brightness, an unusual galactic structure, or a puzzling redshift, serves as a spur to innovation in theoretical physics. As new data from JWST continue to challenge our preconceptions, theorists are pushed to refine and sometimes radically reimagine the fundamental laws that govern the cosmos. This iterative process of hypothesis and revision is at the very heart of scientific progress, transforming each anomaly into a stepping stone toward a more complete understanding of the universe. The revelations from JWST have profound implications for future astronomical missions. The deep field images and detailed spectra serve as both a foundation and a roadmap for the next generation of space observatories. Armed with increasingly sophisticated instruments, future missions will be tasked with extending our view even deeper into cosmic time, exploring the phenomena that lie at the fringes of our current understanding. The challenges and mysteries uncovered by JWST are not endpoints but rather milestones in an ongoing journey, a journey that promises to reshape our knowledge of cosmic origins and the evolution of galaxies. In the face of such profound discoveries, the spirit of scientific inquiry must remain unbridled. Every unexpected observation, every anomaly in the data, serves as an invitation to explore further and to question even our most cherished assumptions. For experts in the field, the pursuit of knowledge is not merely an academic exercise, it is a passionate quest to unravel the mysteries of the cosmos. The challenges posed by these observations are not roadblocks but opportunities, urging us to refine our methods, challenge our theories, and ultimately expand the boundaries of human understanding. As we continue to analyze and interpret these extraordinary findings, it is impossible not to reflect on the legacy of the pioneering astronomers whose work paved the way for today's discoveries. Their visionary theories and meticulous observations laid the groundwork for the revolutionary insights we now enjoy. Standing on the shoulders of these giants, modern astrophysicists are inspired to push ever deeper into the mysteries of space, carrying forward a tradition of inquiry that has transformed our view of the universe over generations. Looking forward, the future of cosmology glows with promise and uncertainty in equal measure. The data streaming from JWST not only resolves long-standing puzzles but also opens up entirely new realms of inquiry. With every new observation, the narrative of cosmic evolution grows richer and more complex, presenting fresh challenges to our theories and inspiring innovative research. The quest to understand the cosmos is an ever-unfolding adventure, a perpetual exploration of the unknown that will continue to inspire future generations of scientists. Ultimately, these discoveries stand as a tribute to the enduring wonder of the universe. The intricate patterns of light and shadow, the rapid emergence of cosmic order, and the tantalizing hints of phenomena beyond our current grasp all serve as a cosmic ode to curiosity and exploration. As we chart our path forward through the vast tapestry of space and time, we do so with a renewed sense of purpose, an unyielding commitment to unraveling the mysteries of creation and to celebrating the profound beauty of the cosmos.